So today we're going to continue working through solving square roots and other radical equations. Notice that in order for us to have a square root problem, it doesn't have to even physically have a square root. It doesn't have to have that symbol. Remember, raised to the power of 1/2 is the same. And remember that the key of what we're going to do today is backwards order of operations. Order of operations, GEM-DOS, multiply, division, addition, subtraction. Our goal is to undo everything and get rid of everything until our variable is all by itself. So just keep that in mind. And let's look here at example 2, the first problem here. So notice that this entire variable and the -2 is trapped within grouping symbols, hence the G for grouping symbols. So I need to undo anything that's happening outside of it. Anything in the front here and anything outside there. But there isn't anything. So the only thing that needs to be gotten rid of is this power of 1/3. And what we can do there is effectively, when we raise it to the reciprocal power, raise it to the 3/1. When we do that, whatever I do to one side, I do to the other. So 5 to the 3/1. Now, most of you realize, 3 divided by 1 is still 3. So I don't even need that 1. So on the left side, the parentheses go away, and so does the 1/3 power. Over on this side, 5 to the 3rd power is 125. And now the last thing I need to do is add 2 to both sides. So x is 127. So what were my steps here? Number 1, I take the reciprocal power. Reciprocal power of both sides. Now, that's not always the first step. The first step is getting rid of any addition, subtraction outside, getting rid of multiplication, getting rid of any grouping symbols or exponents. So here we got rid of the exponents first. Then I'm going to work inside the grouping symbol there. Lastly, I added 2 to both sides to get this. Now let's just do a quick check just to make sure we're golden on this. So x minus, undo that, 127 minus 2 to the 1/3 power should equal 5. Now, as we check this, now we're doing the order of operations. The order of operations says do inside the grouping symbols first. Okay, great. I'll do that to be 125 to the 1/3 power equals 5. At this point in time, don't cube both sides because we're not solving for it. We're just checking. So order of operations. So now what I'm going to do is take the cube root of 125, which is 5, equals 5, and I'm golden. Now, as we look at problem B here, the major difference here is I've got 3 things happening to x, but only x is being raised to this power. So I need to isolate the x to the 3/2 before I do the exponent reciprocal there. Over here, the entire binomial was being raised to the power, so I had to get rid of that first. So paying very close attention to what is happening. So in this case here, I first have to get rid of that 5, the subtract 5, by adding 5 to both sides. 4 to the x, and I'm going to change my way of writing it, 3/2, just so that it's a little bit more clear, easier to write out. I add 5 to both sides to get 108. Now I need to get rid of that 4 right here because the 4 is not being raised to the power, only my variable. So when I get rid of the 4 by dividing, I get 27 here. Now at this point, I'll show it just to show what's going on, but I need to raise this to the 2/3 power and raise this to the 2/3 power. Why? The 3's drop out here, the 2's drop out there. So I'm left with x equals, and there's a couple different ways to interpret this. Number 1, you can just plug all this into your calculator right here to get an answer. But let's figure out how we can do this without the calculator. Remember, the 3 is the denominator, so it's the cube root. So I'm taking the cube root of 27, and then I'm going to take the square. And you're saying, but wait, can't I write the square inside? Sure. But if you did that, then you would do 27 squared, which gives you a very large number. Then you have to do the cube root of that, and that's difficult to do mentally. But cube root of 27 I can do. That's 3, and 3 squared is 9. This becomes 3, and squared is 9. So there we go. Quick check over here. So 4 times 9 to the 3/2 power minus 5 equals 103. Now, evaluating this one here, the square root of 9, because the 2 is in the denominator, that's 3, and then square the 3 to get 27. So 4 times 27 minus 5 equals 103. Order of operations says I'm going to do multiplication first. Notice we're doing the order of operations now. We're not undoing. Here we're undoing, and here we're doing because we're simplifying. So this one here gives me 108 minus 5 equals 103, and 103 equals 103. Ka-chow. All right, now this problem is where checking really comes into play. And we'll explain why momentarily, but what we're going to see is that every so often we're going to come up with or get what's called an extraneous solution, where mathematically we get it, but if we plug the number back in, it doesn't work for whatever reason. Now, sometimes in real life, when we are solving a problem, just take, for example, you were graphing and you wanted to find out how long it took for a ball or something to hit the ground, and you said, oh, look, it took 4 seconds to hit the ground, but then mathematically you got another answer. Oh, over here is -3, whatever. So, oh, this means going back in time right there, but I can't do that. So mathematically I got 2 answers, but practically only one of them is the case. Only one of them is the case. Now, what we're going to see here, though, is not that we're going to have 2 mathematical answers that don't make sense practically. What we're just going to see is we're going to invent a new answer all of a sudden. So that's what's going to happen here. Notice that I have a variable on both sides. Here's my x and here's my x. So I have to isolate the x, and that's tough. So I have to choose whatever method I can. Well, I'm going to get rid of my radical as best as I can. So on this side, I'm going to square it. Now remember, whatever I do to one side, I have to do to the other, and I have to do it to the whole side. Do not distribute this exponent. We are not saying x squared minus 1 squared. This is a binomial. So on the left side, though, we end up getting x plus 1 because the radical and the root are inverses. Over on this side, we have to do FOIL, double distribution, or whatever. So in this case, x squared minus 2x plus 1. Where did that come from? Remember that x minus 1 times x minus 1, and double distribution to there, double distribution to there, and you get that trinomial. Now, I clearly see that I am now in quadratic territory. So I need to get my quadratic in standard form in order to solve it. I can use and then figure out what I'm going to do there. So I'm going to subtract 2 things. Number 1, I'm going to subtract this x from both sides, and I'm going to subtract this 1 from both sides. So when I subtract this x from here, I get -3. So x squared minus 3x. Then when I subtract this 1, 1 minus 1 is 0. So that's gone. Like so. Again, just to show you if you need to see that, -1, those drop out. This minus x and this minus x gives you -3x. Now, how can we solve a problem like this, which is not Maria? Remember, every time you come to a situation like this, our first instinct should always be GCF. Check to see if there's a GCF first. Before you snowflake, before you do quadratic formula, anything. GCF is the most important thing to check for first. So when you GCF, you get this. Now I can use the zero product property to split these up. And the 2 problems I get are x equals 0 and x minus 3 equals 0. Isolate the x here to get x equals positive 3. And generally, this is the part where we put a ring around it and commit to it, right? Aha, aha. We say this, and we're like, yay, we got 2 answers. But here is the problem mathematically. If you remember what we did, in order to isolate up here, I needed to square both sides. And look what we introduced inadvertently. I now have an x squared term. But look, this is linear. X to the 1 power, which gives me 1 solution. But since I multiplied everything by x, I now have potentially 2 solutions. So at this stage, I introduced an additional variable that wasn't there before. I introduced a variable that wasn't there before. So that's why one of these is actually a false answer. So I'm going to check both of them to see which one actually does work. Again, it's called an extraneous solution, and I'm going to check both of them. So first, I'm going to check x equals 0. Now, both of them could be wrong for whatever reason, so I'm going to check both of them. And not just check one and then say the other one's right if it doesn't work. All right, so 0 plus 1, when I substitute in for the x, equals 0 minus 1. Order of operations says 0 plus 1 is 1, and the square root of that is 1. And 0 minus 1 is negative. Oh, that's not a true statement. That's a false statement. Not true. So that means 0 minus x, or 0 equals, x equals 0, is actually not a solution. I'm going to test the other one to make sure it works. So let's see. We're claiming that x is actually 3. So try that in. X equals 3. 3 plus 1 equals 3 minus 1. And finish this up. The square root of 4 is 2, and 3 minus 1 is 2. Oh, good. It does work. So I've introduced a second variable by taking the square of both sides, which now creates a problem where one of them could be false. Technically, they both could be false, or technically they both could be right. So I'm just going through to check to see if I introduced something that was false. All right, our final type of problem that we're going to look at is when we have 2 radicals. I'm going to show this to you. You're going to cry a little bit, but we're going to do it, see how it works. All right, what do we do? If I were to square this side right here, I would have to take into account that this is subtraction. So it's not really going to get rid of the radicals. But if I take that to the other side, so there's a lot going on. So let me just show you the best thing to do is what we're going to do first is isolate one radical. Isolate a radical. So I'm going to add the radical x to both sides. Because if we see here, now radical x plus 9 is isolated. And over here, I get radical x plus 1. Notice the plus 1 is outside the radical. Now, in order to get rid of the radical on this side, I'm going to take the square of both sides. That's going to introduce a problem on the right side, but we'll get to that as we go. So on the left side, the inverses cancel each other out, and we're left with the radicand. And I'm going to jump to this and show you where that comes from in just a moment. And you say, wait a tick, how did you get that? Well, let's just show that work on the side here, recalling that radical x plus 1 times itself is going to use FOIL or double distribution. Here is x times x. Excuse me, radical x times radical x is just x. Next, I have x times 1, or excuse me, radical x times 1 and 1 times radical x. So when you combine those, you get 2 radical x. And lastly, we have 1 times 1, which is a 1. So, generally speaking, we do get squares, but the square of a radical kills the radical. So that's what we have there. Now what? Our goal is to isolate the x's. So we need to get the x's by itself. What happens though? What do you notice on both sides here? There and there. What happens when I subtract x from this side? Ah, it drops out over there too. Ka-chow. Nice. Now I have to get this x, which is trapped inside a radical by itself. So now we're going back to the very first problem we looked at last lesson. So I'm going to subtract 1 from los dos lados to get ochito loquito right here. And I get 2 radical x. Now I divide by 2 on both sides. And I get radical x equals cuatro. And now I take the square again. Doesn't this ever end? And the answer is, we're done. We're done. We did it.